In this presentation, I show you a new model for correcting images for individual differences in color appearance. The way in which we experience colors depend on different factors, from optics to cognition. Means that conch ratio, as well as environment, age, or the lens pigment density can impact how people see colors differently. The growing interest in correcting visual displays for these differences, especially through monitor calibration, has focused on correcting differences for spectral sensitivities variability. So, focusing more on the cone receptors variability. However, these sensitivity differences do not predict the substantial individual differences in color appearance, so they don't equate images for appearance. In our work, we design algorithms that adjust images to directly correct for individual differences in color appearance based on the measurement of hue percepts of real observers, so without correcting for spectral sensitivity. The goal of the correction is that to vary the colors in images so that two observers looking at two different images, each of them tailored on the hue percept, should show better agreement about the colors they are experiencing. So the physical stimuli are different, but the perception of colors is the same. The first step was to measure perceptual differences of real observers. So we test 19 real observers with an experimental design of U4 identification for the 8 hues, so 4 unique hues and 4 binary hues. The task was a simple perceptual task. People should identify which was the best example of the color test. So in this case, for example, pure green or the pure balance orange. They can move from each chip to the other, as well as in each chip. So they can point with the mouse inside each chip, and they can see all the possible hues that they can choose of. The 4 squares in the middle were just showing the colors the observer was pointing at. Our experimental design was based on the EKL8 color space. And here we can see how the 19 observers' individual hues vary a lot from one to the other. Each patch is a different observer, and some hues vary more than others. This variability can be seen also in this palette, but before I can show you how we apply this measurement on the algorithm we created. The first step was to identify a standard observer made by the average of all the observers tests. For each pixel RGB, we got the corresponding hue perceptual angle. So the black line is the standard observer. Then we made the inverted process for each observer. So from his or her hue perceptual angle, we got the corresponding pixel RGB values. In this case, is the red line. So this is only for observer 1, for example, and we can see that the variability is greater, especially at this part and this part of the color spectrum. But we made that for all the observers, and we can see that the variability is great from one observer to the other. In this palette, we can see that the first column is the standard observer focal colors patch, and each column is one of all the 19 observers we test. The rows are each hues we test. So even though the rendering of the colors will not be the real one in your displays, we can say that the variability across the observers is great, and some hues are subjected to variability more than others. The last part is to apply this algorithm to the correction of images. So I reported here a reference image, which is the original one, and 3 equate images to the percepts of 3 different observers. So we can see that the variability is greater, especially in some part of the image, like the skies, the ground, or the building here. But this is how 3 different observers see the reference image. The idea is that we can equate the images in order to have different stimuli, but then the perception of the images will be the same across the observers. So we can apply this algorithm to color calibration, data visualization also, and to test and understand efficiency in communication, to see how color perception and cognition are strictly linked. To sum up, the large individual differences in color percepts introduce substantial variability in how different observers experience the same stimuli. These differences can be modeled and corrected in displays, in different displays of the same observer, and as well as on different displays across all the observers, to minimize as much as possible the variability in the reported perception across observers. The observer calibration is based on simple measurements that can be readily implemented on most visual displays.